We're going live in a few minutes. Laughing face.
Presented by Page Wizard Games, Learning and Entertainment. It's that time, everybody. Time for more entertainment and fun with your favorite computer scientist, Dr. Daniel Page. Welcome to Dan Plays, where Dan has fun with friends and we talk about all sorts of fun things, including computer science and everything under the sun. No barriers, just fun. Check out all the fun rewards and supporter access at the links. That's enough for now. Let's get started. Come on, Dan. Let's get started.
Hello everybody, I hope everyone's having a beautiful day. I want to welcome you onto the stream here today. So before we get started today, I just want to give you a heads up of what we're going to be covering today. So first, if I didn't get a chance to say it already, I hope you're having a beautiful day. I think I did already, but what we're going to cover today is some more combinatorics, some basic combinatorics. I would argue that the difficulty for this lesson is somewhere between high school to college or university. So there's going to be some elements of this that would most certainly fit, say if we're talking about like, say the Manitoba curriculum, some elements of this would appear in a pre-calculus class, for example. Some elements of this would appear in a university discrete mathematics class. So there's a nice blend here. So I'm hoping to give you something that, so if it's either been a while since you've seen some of this stuff, or you've never seen it before, you might find it's pretty helpful, just generally, whether it be for review purposes, or for educational purposes, just more broadly. We have ourselves a great time over here. So before we get into everything here today, just a couple quick things to mention is that the notes for today's lecture will be available on patreon.com/pagewizard. It's just available at the supporter access tier, which is the same level that you also get access to the other previous live lecture notes. Sorry, I'm getting really excited about this. So say you have an enthusiastic student or family member, or maybe you are very enthusiastic or excited about computer science, or the mathematics around computing. If you're interested in that, that's most certainly the kind of stuff I focus on here. So consider looking at patreon.com/pagewizard if you want more details about some of all forms of rewards that we have, including getting your name in the credits to making suggestions for what I'll cover in the future, along with access to the notes and the other materials that I've produced, varying at different tiers. The more higher up the tier, the more broad it is. So other than that, and I must stress that these costs are ridiculously low. So keep in mind that by supporting, you're not only getting resources, you're also supporting us here at PageWizard Games Learning Entertainment. And I must stress that all of this is supported via Patreon. There isn't like some other revenue stream coming in here from some university or something. You know, that no such thing is happening. So we are an independent academic institution, not in the same sense as a public one, but we're more of a, I guess it would technically be a priority. Sorry, I'm just making up words here today. Either way, the best way I could describe it is we're an academic island that's separate from the universities and college system. So, namely, I'm interested in teaching computer science and mathematics. I'm not going to have anything fancy-pantsy here. Mainly thing is that we're here to learn and discuss all sorts of academic ideas. But you don't have to worry about me coming for you for some weird code of conduct or some weird things that the universities do these days. Sorry, I'm just on a roll here today. The point I'm getting at is that the PageWizard Games Learning Entertainment is an independent academic project. It's not anything attached to a university, and it is the sole stream for which I do my content here. So just be keeping that in mind if you think that this is worth supporting, an independent academic resource outside the universities that provides same or higher level content than some of these institutions do. Please be considerate of such a thing. If you would like more of these kind of things to exist, please consider supporting. I put a lot of work into our lectures and the materials that we produce here, and all the other content we produce. It's pretty wild, and it is exciting. So I'm hoping that anybody would be curious about jumping on and joining and supporting. That's wonderful. I'll be glad to see that. So that's enough about talking about Patreon, but just simply, if you don't have the money right now or you're not interested in doing it that way, of course, consider liking, subscribing, sharing. I'm not going to ask money of you, okay? So one other thing I want to mention of you is that whenever the chat is visible on the screen, the text-to-speech will go audibly through, if you're on Twitch. But whenever the chat isn't visible, I still hear and I also see the chat. So just be aware of that. So just because it doesn't show it on the screen doesn't mean I'm not seeing or hearing it. So if you have questions during the live lecture, please throw her in the chat and I'm happy to address it. If it's something a little bit more complicated, we'll maybe look at it in between the main things we're covering. Other than that, I most certainly could say that if it's something smaller and clarification, I could deal with it on the spot. It's pretty easy stuff. But yeah, no, I do want to mention one other detail, that Tuesday next week, I may or may not have a live lecture. This is because we're around Christmas time then, and I may want to take one of those days to actually relax and try to do something else other than work, okay? So hopefully that is something that's understandable, but we'll see. We'll see. If I get in the mood to get the lecture going and everything like that, we'll most certainly do that. But I will have a Christmas video as a supplement to this next week. So hopefully you'll appreciate that. We do a lot of work on over here. Lots and lots of time goes into a lot of these lectures and preparing this stuff so that, one, you don't have to worry about paying hundreds of thousands of dollars for it. You can get it for magnitudes less. But at the same time, you also get the opportunity to learn from somebody you can trust that isn't just simply going to be gouging you for money or expecting you to compel to somebody else's beliefs. Because I'm very much against those type of things. We're here to talk about computer science and math. I'm not here to tell you, yeah, look, you need to you have to believe X, Y, and Z to be at our school. I don't like that idea. I think that when you do stuff like that, it corrodes the nature of an academic institution. Instead, it becomes more of an activist platform. And I'm all about academic excellence here. And that means we also get to have fun. So I don't. it's not about what you look like and all of that stuff. That stuff I don't care about. Okay. Unfortunately, there's a lot of universities I can't say that so much about these days. Unfortunately. So that's a little bit of a Debbie Downer. But let's get into something more exciting here for today. We're going to be talking about some more counting and combinatorial discussion here. Namely, we're going to be talking about more combinatorics. Sorry, I'm getting really excited here. So, sorry about the downing. I have to make sure it's clear to everybody that right now the stuff we do here is independent. It is not associated with any. There is no big university backing what I'm up to here. Okay, so. Do you consider it and support a local small business? Because that's what I am and what I do here. So I must stress that it's just me and whomever supports my work. So if you want to support that work, tell your friends to come on out. Of course, subscribe, like, tell your friends. And of course, if you want to do more beyond that, if you can, that's okay. Otherwise, it's totally not okay. Not okay. What am I saying? It is totally okay if you don't have the resources to do that. That's okay. But be very considerate of the idea of maybe if you want to get the resources beyond just the video lectures, supporting on Patreon or Subscribestar. So you can find the links on the page. Okay. So, anyways. And I'm just on a roll here today. I'm just grilling all sorts of things. Hopefully you find this somewhat entertaining. I'm happy to talk about a lot of this kind of stuff. I taught in the universities for about a decade, and some parts of it very much disappoints me these days. I think some have kind of escaped their principles, and I think that a lot of them are rewriting what their principles are on the spot, and they're going to make a lot of errors in that process. I don't know what exactly they're going to do, but all I know is that I've seen enough things that concern me. Some places are fine, others not so much, but that's a whole other discussion for another day. Today we're going to be talking more about combinatorics, and namely we're going to be going back to the basics, okay? So previously we talked about things such as the pigeonhole principle, and we also talked about its lesser known cousin, the averaging principle. And we've seen how we can use those, but also how we could prove them too. So for example, we derived the averaging principle from the case for integers, and we also proved it is in fact true. But I want to go step back. We want to go back to some even, I would argue, or another set of counting tools or counting techniques. We're going to be talking first about what we call the addition principle and the multiplication principle. And then we're going to be talking about, well, so in tangent with those, we'll talk namely about counting elements in sets. So you don't need to know a whole lot about set theory here. I'll be parsing anything that involves set theory a little bit carefully for you, so please don't worry. I'm not going to expect a lot of set theory from you, because I haven't really done actually, I do have a set of videos on set theory on the channel, but I made them some time ago, and they don't have the same production quality as I have here. So, that being said, what we're going to do here today is we're going to first talk about how we could count elements in a set. Namely, we're going to do this in relation to what is called the addition principle. Then we're going to see how this generalizes as something called the inclusion-exclusion principle. And then we're going to work over to the multiplication principle. We'll see how we can derive all sorts of counts of different kinds of objects in relation to the multiplication principle. So, for example, we're going to see some combinatorial objects called permutations, namely permutations, k-permutations. Then in addition to this, we're also going to see combinations such as k-combinations and k-combinations with repeats or repetitions. And we'll see how to derive how you get these counts. We'll see some examples as well, okay? So hopefully you're excited as I am. Whenever we get it's sort of one of the fun things about this topic is that very often in like when you begin learning things in your education, like I'm talking like right from when you're like yay high, not very tall. One of the first things you start learning about is counting, like in school, like how to count the first 10 numbers, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Counting is intuitively something that you're used to doing, but at the same time, it's also something both elementary, pun intended, but it's also something rather rigorous and careful that you have to do. Some would say counting is a very easy thing to do. I would argue that counting can actually be quite challenging. So it can be both. It depends on what kind of things you're counting. I would argue that many of the things we're going to talk about here, they have a very intuitive grasp around them, but I'm hoping I can convince you that it's not just as simple as just, oh, it just exists and that's all it is. I'm hoping that we'll be able to wrangle ourselves around some of these ideas so that they're not just common sense, they're actually something you can pin down and prove, okay? So, and that's what makes the difference that I would argue between just knowing fun formulas versus actually understanding the M word around them. The mayonnaise or mustard, the dreaded M word. How do we understand what's actually going on with that and where the ideas come from? Sorry, I'm getting really excited. I give you a little bit of background when it comes to this topic. So combinatorics is one of the things that really got me excited about some of the more advanced, specifically algorithms around combinatorics. So for example, generating what they call combinatorial objects. Like I mentioned a couple actually here. Like permutations, like set of all permutations, set of all combinations. Algorithms like this are actually some of the initial things that really got me excited about studying algorithms. Beyond just simply saying, oh yeah, look, there's this stuff, there's algorithms, isn't that exciting? I just thought they were fascinating because of how careful you have to be about enumerating all of those types of objects, because they're what we call in the computer, the algorithm circles, who would call this output sensitive, because as the name suggests, they're combinatorial, and generally their description, when you describe the object itself, tends to be exponentially large. So, meaning that the algorithm is going to have to deal with the fact that your answer is going to be exponentially large, so that means that the amount of time it's going to take to compute those answers is also going to take a while, potentially. So you want to try to do this carefully so that you're mitigating the fact that, oh yeah, you're creating really something quite massive, but at the same time, you want to do it fairly efficiently in the context of that. So that's just some background about me before I got really into combinatorial optimization, which is otherwise it's kind of its cousin, of course, or if it can be thought of as a broader category. But we're going to be starting really at the basics. We're not talking about algorithms so much here. It's more about the combinatorics, they're just counting, not necessarily how you count them, which some of those recipes will come up in this, but most certainly it's more about just how to count. and some people might find that just a little bit strange to hear from me. But that's really what it is. So what I think would be a good place for us to start when it comes to talking about basic counting principles is namely counting elements of sets. Counting elements of sets. So I think this is a rather good place for us to start. We're going to start talking about counting elements of sets. Namely, we're going to be looking at our first of the two basic principles for counting that we're going to discuss here. I thought it would be a good idea I give you an idea where we're going with this. So suppose I give you a set. Now a set is just you can think of it as a collection of objects where there's no duplicate objects in the set, and we don't care about the ordering of them. So we call the things inside the set an element, or elements per plural. And you can imagine, for example, that you have a set and it has elements in it. Now I must stress that we're going to pretend that these are all different elements. These are all distinct objects that are in my set. They could be, for example, strings, they could be numbers, they could be all sorts of things. They could be me, I don't know, at least on an abstract level. Okay. So you can imagine I have here 6. So suppose that I wanted to know how many elements are in a set. Now, of course, I could go through each one counting one after the other, right? Now, imagine that instead of suppose instead that I gave you 2 buckets. 2 buckets. And suppose that one bucket has 3 elements in it. Another bucket has 2 elements in it. And let's throw a third one in here, just to make this fun. Suppose I have a third bucket with 1 element in it. Now, what if I wanted to answer the question as follows? Suppose that I wanted to know how many elements were in all 3 buckets? Well, naturally, one way you could do this is you would ask, okay, there's 1 in here, 3 in here, 2 in there, so you just add them up. Now, one thing that's really important about the way, there's something rather implicit that I did here, right? First, a set doesn't necessarily have it where all the, like you can imagine these as 3 different sets, but there's a presumption that I've made here. First, that each one of these guys are distinct. They aren't actually 2 in the exact same kind in 2 or more of the buckets. So for example, suppose that this element actually existed in, say, this bucket too. If I were to do that, would I end up getting the correct count by following that process? No, because I would overcount this element by 1, right? Suppose that, for example, this is like the number 1, that's 2, 3, 4, and this is 5, but 5 appears both in this bucket, but in this bucket as well. So suppose it's in this one, but it's also in this one too. That's something that's possible with a set that you can't do with a bucket like this, unless you literally were only caring about labels on these items, okay? But the point I'm getting at is that we're making a presumption when we put the objects into the buckets, is that the objects behave in a way that they can be put into a bucket, but they don't actually cause it to exist in more than one bucket, in the way I've implicitly laid these out, right? So sets don't necessarily have this property. We need to ensure that we actually represent that carefully. So what we would describe, what I've just described here for you, is that when I look at this set versus this set, or this bucket against this bucket, they don't have any elements in common amongst each other, right? So we would call these 2 together, they're mutually disjoint, meaning that there's no common elements between the 2. Likewise, I could say the same thing about these 2, and I could also say the same thing about these 2. So what we would do is we would actually talk about this in terms of sets a little bit more carefully. So let's write something down about this. And this brings me to talk about the addition principle. So here's the addition principle. So this is a theorem. We're going to prove it. So consider any finite set A. So A is the name of the set. And remember, the set consists of elements. Now, I didn't say anything about it having no elements or having elements. So it could be empty, technically speaking. So this set is going to have a property. It's going to be similar to our buckets. That is the union. Now, I'll explain what that means in a moment. The union of K. So I'm going to imagine I have K. So think of K as the bucket. So K would be 3 in our example. K distinct pairwise disjoint subsets. A1, A2, A3, all the way up to AK. So there's actually going to be K of these subsets. And let me walk you through carefully what this means. So the union, what it means is that you're taking the elements in all of these, you throw them into one super bucket. So for example, like I had all 3 of these buckets. Imagine I took all the elements and I dumped them into one super bucket. Now, the thing that happens when you perform a union operation in set theory is that you don't count the duplicates. So duplicates just sort of evaporate. We don't care about multiplicities of elements. Likewise, we don't care about the order in which you do it, okay? So first, if I put all these elements in these sets go into this one, just like I dump all my elements into one bucket, I just don't care about the duplicates. So it means that I just simply imagine they just don't exist, right? So I just simply could just toss out any duplicate I run into when I'm doing this process, or just simply ignore them. But we don't attribute them to being a part of the count of the elements in the set. So I have K of them, but they're pairwise disjoint. Just like when I talk about the buckets, did you see that it was possible for me to have an element that exists in 2 buckets simultaneously? No, right? Because one had to be in one of the buckets, right? It couldn't be in 3 different buckets or 2 different buckets. It had to be in 1 bucket. So that means that when I look at my different buckets, so these are actually the buckets here. If I look at any pair of buckets, they don't have any elements in common amongst each other. So that's what pairwise disjoint means. So that means that if I were to take them together, there should be no elements in common amongst them, okay? So there's k of them, and they have this pairwise disjoint property. So it's just like our bucket scenario. So what does that mean then? So remember, we just talked about how we would count this then. Well, how many elements are in A? So a common way to denote the number of elements in a set is using these vertical bars. So this is noting what we call the cardinality or the size of the set A. So the bars here, these denote the size or cardinality, if you want to be fancy-pantsy like me sometimes, the cardinality of the set. This notation is very common with knowing the size of something, like a length of a string. This notation is fairly common. So if I want to get the number of elements in A, that's what this means. What I do is I sum over the cardinalities or sizes of the subsets. And this is exactly what we just described before with the buckets, right? All this is saying is you go across each bucket, you count up how many elements are in each bucket, right? That's what it says. And then this addition principle is saying that actually equals the cardinality of A. And remember, it's because of this condition in play. If we didn't have that, as we're going to revisit, we can't necessarily say this, okay? So we're going to actually prove this theorem. We're going to use mathematical induction to do this. So we prove the claim via mathematical induction. So usually a good idea when you're proving something by induction, you need to state what exactly you're proving and what you're proving on. So in our case, notice that I have k distinct pairwise disjoint subsets. So a natural parameter for me to perform induction on is k. So notice that the statement, when I alter k, seems to be the real game changer here when I want to prove this statement, because k is the only variable other than the sets themselves, which we must presume that they're arbitrary, right? This is the thing that seems very natural to iterate over when we talk about induction. So for each k greater or equal to 1, we're going to let the statement S of k, we let S of k denote the statement. So this is what we're going to prove. We're going to prove the following statement. So you're going to see that I'm just going to reframe this. So S of k is if a finite set A, equals the union of k pairwise disjoint subsets A1, A2, ... AK, then it has to be that something like this follows, right? Then the size or cardinality of A is equal to the sum from I is equal to 1 to k of cardinality of AI. Right? If we could prove this, then we're done, right? So let's now go through and go about this. So if we can prove this for all k greater or equal to 1, then we're done. Piece of cake, right? So what's the first thing we do in an induction proof? Well, think back to teaching Miss Kitty how to climb a ladder. So what's the first thing you do? Show Miss Kitty how to climb up a first couple rungs, or as many rungs as Miss Kitty needs. They make it easy enough to show how to climb any arbitrary 2 or 3 rungs or more. Namely, go from one arbitrary step to the next arbitrary step. If we could do that, then logically speaking, we could show Miss Kitty how to climb up any number of steps on the ladder, at least if we're thinking about this from an induction standpoint, not from a stubborn Miss Kitty standpoint. So let's see what happens. And then that way Miss Kitty can go nap in the bed, and we proved our statement. So we're going to prove our base step. We're only going to need one here, namely for k is equal to 1. So S of 1 says A is a set that equals one subset. What's the one subset? What is it? What is it? We only have one possible subset. Well, in our statement, we would call it A1, right? But what does that mean if there's only one subset and it actually equals? So if I take the union of all of these subsets, I get A, right? So if I only have one bucket, which is what A1 is, what is this when I take all the elements in A1 and I union them all with the other possible subset, which in this case there's only A1? Well, it's just A, right? That's all it is. Then A is equal to A1, and because this is the exact same sets, that means that it has to be the case that A, the set A, is equal to the set A1, and so they have to have the same count, right? And so the cardinality of A is the cardinality of A1, and S of 1 holds. So we've proven for k is equal to 1 the addition principle. Now we would like to be able to go an extra step here. Namely, we want to do this inductively, right? So now we got the more interesting part of this claim. So now we have the induction step. So we're going to prove given S of m. So if S of m, then S of m plus 1. So we're going to fix some integer m, which is going to be greater or equal to 1 because we proved it up to 1. So that's why I picked 1 there. You gotta imagine it like I'm climbing up a ladder, but I only go up to and until where the induction needs to begin. So we're going to fix that and assume that Sm, so S of m, which is going to be, it says if a finite set A equals the union of m pairwise disjoint subsets A1, A2, all the way up to AM, then the cardinality of A is equal to the sum from I is equal to 1 to m of the cardinality of AI. Right? That's what S of m would be, right? So what I need to do is that if this is the case, then I want to show that S of m plus 1 follows from it. So we're going to assume this holds. This is our induction or inductive hypothesis. I'll point out when we use it. Then we prove that, now S of m plus 1 is just simply this, where I replace everywhere I put m with m plus 1. Prove that if a finite set A equals the union of m plus 1 pairwise disjoint subsets A1, A2, all the way up to am plus 1, then the cardinality of A is equal to the sum from I is equal to 1 to m plus 1 of the cardinality of AI for each AI. So we got to, actually, I don't want a period yet. I need to say that this follows, right? Then we prove that this follows. So this is going to be the setup for our induction step. So now let's head over here and let's proceed. Now, this is the great part, is that induction makes this so easy to do sometimes. It's a little deceptive. Like, okay, maybe I shouldn't say deceptive. It's more that it gets you excited just how versatile induction can be, that it makes you almost worried that you're applying it incorrectly, but you're not. So here we go. Here we go. So now watch this. Now this is where I'm going to use a little bit of set theory here. So I'll explain this very carefully. So by definition, A is going to be equal to the union of A1, A2. This is what this U represents. It means union. So it means I dump all of the elements of these two into one bucket. I don't care about the duplicates, so I'm just going to pretend they just don't exist, or I just throw them out. And I'm going to do this over all of the subsets. So remember, just think of these as buckets. In fact, that intuition will be very helpful for this proof. So I have all of them. Remember, this is what it says, is that A is the union of all of these subsets. And we said that they're pairwise disjoint, right? So let me write this in set theoretic terms. So what it's saying is that if I give you any two subsets, AI and AJ, it has to be that these, when I look at them, they have no elements in common with amongst each other, meaning that it is empty. So this is the empty set, meaning that there are no elements in common. So this is what we'd call intersection. So these are the elements that would be in common amongst each other. So meaning that they exist in this set and this set. You know how I talked about how I tried to imagine that there was an element that could exist in both buckets at the same time? What this constraint is specifically saying is that if you looked at these two sets, it must be that the ones that are in common, which would be a resulting set after this operation, there's none in this set. That's all it says. There's none in common. So this is true for all. So I got to do this over all of the i's and j's. For all i's equal to 1, 2, all the way up to m plus 1. And j is equal to 1, 2, all the way up to m plus 1 whenever I is not equal to j. So what I'm saying is you can imagine this, you're just looking at every one of the possible pairings of these like we did in our example with the buckets. And I said that there's none in common. That's all this is saying. That's all it says. There's nothing scary about that. It's just, that's all it's saying. So now, I'm going to, so let me give you the game plan of how I'm going to employ induction here. Now remember, if S of M holds, then I know for M subsets, and these are pairwise disjoint amongst each other, that it has to be that they equal the sum of all the cardinalities, right? Of those is what A would be at that time. So what I'm going to do is I'm going to invent a new set that's going to include something a little bit different. So watch this. So watch this. So let set A prime, so watch this. So I'm going to give that a name. Let A prime be the union of A1, A2, A3. So it's all of the union operations of over all these subsets. I'm going to dump them all into one super bucket. And that's going to be what A prime is. Remember, I get rid of all the duplicates. I don't care about those. They're in common. But the thing is, we don't have any in this case, right? There are going to be no common elements because these are all pairwise disjoint, right? So there aren't going to be duplicates. So notice that both A is equal to A prime union A sub M plus 1, right? Because that's what A is, right? A is the union of all of these up to AM union A M plus 1, right? That's what A is. But A prime is everything up to but not including the last bucket. So A is actually going to be equal to this. And remember that all of these subsets are pairwise disjoint regardless, right? So even if I lumped all of these first subsets all together, then I union this one, they still are pairwise disjoint, so there's not going to be any duplicates, right? So, and A prime intersect AM plus 1 is equal to the empty set, right? The pairwise disjoint. So, what does that mean about the size of this set? Well, the cardinality of A prime union AM plus 1. This is actually going to be equal, because remember, there's all of these elements. They're on their own, right? From these ones. There's no common elements, right? So if I counted them, it's no different than me examining one super bucket with another bucket. And they don't have common elements at all. So it means that the sum of how many elements are in this set here is just going to be A prime, the cardinality of A prime, plus the cardinality of A plus 1, right? Now we have the key ingredients to prove the claim. So watch this very carefully. So to prove this, I'm going to start on the left-hand side of S of M plus 1. And we're going to derive the right-hand side. So beginning on the left-hand side of S of M plus 1. Well, what was the left-hand side? It was the cardinality of A, right? But what does that equal? Well, we established in the previous sentence that that is the cardinality of A prime plus the cardinality of AM plus 1, right? That's what it means. But what does that mean? Well, this, if I unpeel this, what can I do with this? What's this? What's A prime? Well, we know that actually the answer to A prime, right? Because of the induction hypothesis. It's the sum over all the subsets, right? Up to M. Plus the cardinality of AM plus 1. But this is by the induction hypothesis, right? So I just pulled out S of M and I say, okay, well, I know the answer to this one, right? That's what S of M is talking about, which equals this. Now all I'm going to do is just bring this in to this sum, and then we're done by adding an extra term into the summation here. So it's a sum from I is equal to 1 to M plus 1 of each AI, which of course is the right-hand side of S of M plus 1, right? Completing the induction step. Completing the induction step. Are we done yet? Are we done yet? So remember, the whole trick here is that I lumped in this cardinality, this number of elements here into here. It's quite intuitive, right? But am I done yet? Not really yet. No, I have one last thing I have to do, because I have the base step and the induction step. I still have to invoke the principle of mathematical induction to complete the proof. Therefore, so this would go just below this, but I've run out of space below there. Therefore, by the principle of mathematical induction, which is a theorem, by the way, we're using that, S of k holds for all k greater or equal to 1. And that completes the proof. That box over there indicates the end of the proof. So you might say, Dan, why do we need to invoke this? Is that because these are the conditions for which you can apply the principle of mathematical induction? That's what does all the heavy lifting, what we talked about with the intuition around Miss Kitty climbing up the ladder to get to the bunk bed to go for a nap. It's the same intuition, but we're actually using it mathematically. I used the M word. I'm a monster. Which is another M word. Okay. So that's how we can prove the addition principle, and it seems really basic, right? This is some of the more basic things that you probably have ever counted before, right? But we verified it formally. So I want to bring us to another way of viewing the addition principle, that in a way that when we think about things in combinatorics, how we might use this. And I must stress that there's many ways you could use just the cold turkey addition principle. But I want to highlight mostly a higher level version of applying this in plain language. Okay. So here's an alternative formulation of the addition principle. So this is an alternative version of the addition principle. Now, suppose, so instead of thinking about sets and subsets, I'm going to think about them in terms of actions, or you can even think of it like categories even. But I'll like to think about them as actions. Suppose there are k, and I must stress that these must be disjoint. For those that are statistically inclined, I mean independent. But we're using disjoint in the sense that we talked about actually here. There's nothing in common amongst these actions, okay? So that if you did one of them, it wouldn't influence the other ones, okay? K disjoint actions, A1, A2, all the way up to AK. So far we're looking kind of similar, where there are N1 ways to do action A1. There are N2 ways to do A2, and so on, until there are NK ways to do AK, action AK. So one way you can frame this is as a number of possible ways you can achieve something about this. So let me frame it carefully for you, because with a slight tweaking to this, you get what we call the multiplication principle. So I'm going to focus on the addition principle. Then the total number of ways to do A1 or A2 or all the way up to or AK, up to it includes AK, is the sum of the number of possibilities. N1 plus N2 plus N3 plus all the way up to NK, which this is of course equal to the sum from I is equal to 1 to K of Ni. Do you see how this alternate formulation is the exact same thing we just talked about, right? It's the same idea. It's just an alternative way of describing the same thing to you. Do you see that there's one very important detail about how this is formulated? Is it says the number of ways to do A1 or A2 or A3 or A4 or all and so on or AK. Notice there is an or here. So let me show you an example of how you might use an or like that. So here's a cute example I always like to point at every once in a while when I get a chance to talk about this. Okay, so let me give you a cute example of using the addition principle. Suppose you go somewhere for dinner. Suppose you go somewhere for dinner. That dinner's looking a little bit crooked, okay? So the menu has some choices on it for the dinner plate. The menu for dinner has the choice of 3 chicken meals. So these might be like 3 different kinds of chicken dishes. That's what I mean here. 4 beef meals. So these are just plates that have beef in them. 5 pork meals. And 5 vegetable meals. So you're given an opportunity to pick one of these for your dinner, right? So you get to pick your big dish for your dinner. And you have choices from these. So given the opportunity, to pick any one meal, what does that mean then? Well, let's characterize this in terms of the addition principle. Let's think about this. So you get to pick any one meal. So how many are there of chicken meals? So notice that each of these looks like an action in our alternate version of the addition principle. We can get a chicken meal, we can get a beef meal, we can get a pork meal, or we can get a vegetable meal. Do you notice how I use the word or? That's a very helpful phonetic way of remembering when you might need to add as opposed to doing something else. So, what does that mean? So there are 3 ways to pick a chicken meal, there are four ways to pick a beef meal there are 5 ways to pick a vegetable meal. So what does the addition principle tell us? If I have the opportunity to pick any one meal, so I'm picking one, how many are the number of ways to pick a meal? What's the number? Don't overthink this. So remember, you're sitting down at a restaurant. You're going somewhere, you're going to have something to eat. You look at the menu. And you see that, okay, there's these chicken meals, you have the beef ones, you got the pork ones, and you got the vegetable ones. So how many are there? How many ways can you pick a meal here? Well, think of it. You have a menu in front of you. So imagine you have a menu in front of you. You only pick one of them. So how many things are on the menu that you get to pick from? It's the sum of these, right? It's the sum of them. That's exactly what the addition principle would tell you, right? Which is very intuitive. By the addition principle, the number of ways to pick a meal is as follows. It is 3 for the chicken meal, right? 4 for the beef meal. 5. Let's see, what do we got here? Oh, I got the pork one. I gotta get pork in here. I knew I forgot one. Ways. I was looking at the board, I'm like, no one's saying anything. I better bat it in. 5 ways to pick a pork meal. So we got 5 for the pork, 5 for the vegetables. So that means that's 10. That together is 17. And this is really intuitive for this scenario, right? Because you can imagine you have a menu in front of you and you ask how many possible dishes can you get for dinner? Well, you just simply count up how many are there, which is the same as doing one of these, right? Sorry, I'm just getting really excited. Not for the meals, okay? I'm just talking about the counting. So that's an example of applying the addition principle. The key thing is that it's about that you get a choice. It's I do this or I do this. It's not I do this and I do this. Just remember that those are not the same things. And it also matters that these are not related to each other in the sense that if you pick the chicken meal, that it actually, one of these meals is also a beef meal, for example. Like it's chicken and beef. That would be a little bit of a problem, which I'm going to talk about now. So as I alluded to earlier, there are limitations to the addition principle that you need to be aware of. So let's go through an example of what I'm talking about. So we're going to just first blindly apply the addition principle, and then we're going to see what happens, okay? Suppose that I give you, so we have to be careful. So be careful when using the addition principle. So just remember that those sets, those subsets, or actions, they must be disjoint. They're mutually disjoint. So example, suppose that I give you 2 like this. Suppose that A1 is A1, 2, and 3, and A2 is 2, 3, and 6. Equivalently, you could imagine this like I said in my example over there. Imagine these are the chicken meals, and these are the beef meals, and these numbers represent the item, the index in the menu. So some restaurants actually use numbers to indicate the items on their menus. So, sorry, I thought I heard something fun. So these could be the indices of those menu items. So notice that in our example here, we have a bit of a different thing going on here. Do you see what's going on that's a little bit different than something we consider for the addition principle? Well, let's go ahead in and see what happens. So if we apply the addition principle, then what does it say? So it says that the number of elements in A1 union A2 is what? Well, the number of elements in that one is 3, and that one also has 3. Is 3 plus 3, which equals 6. But is that correct or incorrect? This is wrong, right? Why? Well, let's write out what A1 union A2 is. So this is wrong. No, guys, don't do that. Don't do that. Why? Because A1 union A2 is 1, 2. So we got 1, 2. So notice I have 1, 2, 3, and I have a 6. So the number of elements in A1 union A2 is actually 4, not 6. What did I do wrong? What's wrong with this? What did I do wrong? I overcounted. So I'm overcounting by counting duplicates. And remember, we said that we don't count duplicates. That's something we said near the beginning of this. We don't count those duplicates. Those darn duplicates, we don't count them. So what do we do? So what exactly is going on here? So let's think about what this means then. So which ones are common amongst the two? So which ones are in common between A1 and A2? Well, if we take the intersection of A1 and A2, as we discussed previously, I want the ones that are in both A1 and A2, as opposed to the ones that are in A1 or A2. Well, look, when I underline 2, I underline 2 over here. I had 3 over here too. So notice that 2 and 3 are common amongst the two. Those are our these ones I counted. I actually technically counted them twice. It's a mistake. So I have to account for these. I have to account for those elements. So there's our extra 2. So those are our extra 2, as 6 minus 2 is equal to 4, right? And this is the correct count. So does anyone have any ideas of how we can actually generalize this idea? Well, I'll let you think about it, and let's head over here. Okay. So now, this brings me to talking about a theorem that generalizes over the addition principle. Now, because it requires me to give you more set theory, I'm not going to prove it, but I'm hoping that I've convinced you of what and where it comes from. So here's a theorem. This theorem is called the inclusion-exclusion principle. You'll see why it has this name. And I'm going to state it for 2 sets, but the principle still applies more broadly, okay? So you can state it for 3 sets, you can state it for 4 sets, you can state it for any general K many sets. But I think seeing it for 2 sets gives you enough of the idea. So that if you ever needed a more general version of it, you get the idea of how you'd go about it. So if A and B are finite sets, then if I take the union of A and B and I ask how many elements there are, well, we can walk through the same exercise we did over here, just more generally. I can take all the elements in A, the number of elements here, I add them to the ones that I have here, the ones in the other set. But as we previously seen, take note that I did not put any quantifiers on A and B other than that they're finite sets. They may not be mutually disjoint or pairwise disjoint sets. So we're going to have a scenario just like the one we had over here. So I'm going to get rid of the elements just like I did over here that are in common amongst the two. So I take A intersect B. So these are the elements, the number of elements in A. These are the number of elements in B. And these are, of course, the number of elements both in A and B, which you could think of, like we talked about, they're the duplicates. They're the ones that we're going to overcount if we don't get rid of them. Just like in our example over here on this board. So like I said, so this is the inclusion-exclusion principle. You can actually look at our example over there actually as an application. Like we can just apply it directly. So if you just go back to our example and just plop this in, you'll see that we get the same answer, right? We get the correct answer. So this is how you deal with when you don't necessarily know that they're pairwise disjoint subsets. It may be the case that they actually may have an overlap. And this generalizes that principle, the addition principle, over 2 or more sets. So if you had 3 sets, what you do is you would have to go through all the possible, so you add up all of these and you have to go through all the different, like you know how when I had my buckets in front of me, right? I had to go check each one of these, see what any ones are in common there, see if there's any ones common in there, see if there's any common in there. So you'd have to have that in your version with 3 sets, and so on. So this is the inclusion-exclusion principle. Hopefully you find this fascinating. I think that it's pretty helpful to see it at least once in this form. Some people see it when you start studying statistics and probability or probability theory. But if you see it in this pure counting realm, it's very easy to jump over to that one because it's very much the same idea. It's just applying to things we call not to say elements, but they apply to events, and we assign probabilities to those events. But that's the addition principle. Are there any questions? I see some fun things in the chat. Sorry, I had to drink a little bit of water there. But yeah, this is the first principle we're going to play around with. I don't see any questions, so I think we're generally pretty good on that regard. I'm just going to get my book. I'm just going to reorganize things a little bit here. Let's see. Just think about what we would like to cover next. I got some fun stuff here. Let's go with... Sorry, I just have a blast here. Let's see what we got going on. I think we're going to go with the multiplication principle next. So let me just erase the boards and then we'll get into our next part. So if you have any chat, anything funny you want to say, or hopefully nothing too spammy. Okay. If we don't have any questions, I think we'll proceed to our next topic. Our next topic will be the multiplication principle. So previously we talked about the addition principle and also its generalization, the inclusion-exclusion principle. So now we're going to talk about the multiplication principle, which is very helpful for a lot of the kinds of combinatorial objects we're going to talk about. The multiplication principle. And I'm going to state it in this way, but there's at least another way of framing this in terms of sets. I'm going to choose to do something similar to the alternative formulation I did for the addition principle, just to illustrate the point. So here's a theorem for you. So we're going to let integer, we're going to imagine we have an integer k be greater or equal to 1. Suppose k actions a1, a2, all the way up to ak are performed. If there are n1 ways to do a1, n2 ways to do a2, and 3 ways to do a3, and so on up until and ak ways to do ak. The total number of ways to do a1 and a2 and a3 and so on up until and ak is n1 times a2, times n2 times n3 times all the way up to times nk, which of course this is equal to the product. So I'm going to use a big product to denote this. It's the product from I is equal to 1 to k of ni. So this is the multiplication principle framed in the same way that we had our alternative version of the addition principle. If you're wondering how to prove this claim, it's very similar to how you'd prove the addition principle. Just the It's just slightly different, but I think that you get the general gist of how you might go about it if you wanted to carry through the exercise. If you look at how we prove the addition principle, it's a slight tweaking of the ideas, okay? Just now we're talking about doing something and another thing, which connotates that we're dealing with multiplication instead of addition. So the big thing I really want to emphasize for you, as opposed to how we formulated the addition principle, is the fact that we have these ands here. So we're actually performing these actions. So these are all performed. So you can think of this as k steps of a process. And one detail I need to point out about this is that when I do one of these steps, it must be that the number of ways of doing the next step they can't just suddenly change, right? They have to, so if I do A2, it has to be N2 many ways. So for example, A1, if I do something for A1, it can't influence what N2, like N2 can't suddenly be 3 different numbers. It has to be one possible value, okay? So I just need to carefully state that. So just as an example, what I mean is you imagine you make some choices. So imagine you start off here and you're allowed to make some choices for A1. So imagine A1. Suppose that you're supposed to say, okay, I need to make one choice or another choice. And it must be that there are, say if the next action has 3 possible choices, notice that I have 3 possibilities to choose for A2. It can't be that there's one that you have it where it does 3 for one option and then 2 for another option. That's not what the multiplication principle allows you to say. It must be that the choices, as suggested here, they can't all be altered based on the previous choice, okay? So just please keep that in mind. That is a limitation of the multiplication principle. So just be aware of that. So when I say N1, N2, N3, it has to be that this actually does take N2 many times for A2. It can't be that, oh, when I do A1, it has to do that, that sometimes it's N2, sometimes it's like N2 plus 5 or something like that. No. That's not applying the multiplication principle. That's doing something a little bit more sophisticated. So just please keep in mind that limitation of the multiplication principle. So let me give you an example. I thought this would be a rather cute way of going about this. So an intuitive way, let's say intuitive way of viewing this as a k-step process. And it doesn't have to be a k-step process in the way that you might think of literally like I do this, and then I do this, and then I do this, and then I do this. In the same sense, what I'm referring to is that there's some action you take, and then after that, you have to commit to another choice. So that's what I'm referring to. So a common way where this appears when we talk about algorithms and analysis of algorithms, you can imagine, for example, like a nested loop. In a nested loop, you have, for example, a counter variable for each one of the loops, and then it has some number for which it occurs. So when you perform the outermost loop, you commit to some value of, say, for example, if it was I, and then say the innermost loop is j or something like that. You commit a value of I, and for that one, you commit some value of j. And you can keep going through this process. You can ask the question of how many iterations of, say, some code inside or some instruction inside of the nested loop, how many times does that happen? You could directly use the multiplication principle on that, in the sense that you commit to some value of I and you commit to some value of j, and you ask how many ways could value I take a value on, and how many ways can j take a value on. So it's a rather intuitive thing to keep in mind. So let's do an example. So suppose that we're going to go on a road trip. Suppose a person is traveling from Winnipeg to London. I'm referring to London, Ontario, not London, United Kingdom. we're talking about Winnipeg to London, Ontario, via Sault Ste. Marie. So you got to imagine we're going on some trip. So this person is going on a trip. But they're going to be going through Sault Ste. Marie. Now, for the sake of our discussion here, I must stress that there's more than just these number of ways in reality. But suppose that these are ideal routes that we're thinking about, okay? So if there are 3 routes from Winnipeg to Sault Ste. Marie, now you might ask, okay, why 3? Well, it doesn't have to, it's just an example, but at the same time, I must stress that you can imagine that our person's going on a trip. Maybe they're going from Winnipeg, they're going to take the route around, say, Thunder Bay and going up around the Great Lakes, down to Sault Ste. Marie. I've taken that trip. It's quite a trip. It's very beautiful. Some parts are kind of like a roller coaster, especially if you're moving or something like that. So imagine you have a person goes all the way up and around. So I don't know, let's draw a fun picture of this. Suppose I have Winnipeg here, and let's imagine we have Sault Ste. Marie here, and then we have London down here. So you can imagine you have like your Great Lakes like right around here. I'm not going to be doing this too accurate, okay? so you can imagine that one route, our participant goes up and around like this to Sault Ste. Marie. I must stress that this gap's probably a little bit more narrow. Then maybe instead, maybe my person goes down through the United States, up and around to Sault Ste. Marie, like this. I must stress that, like I said, this would be way over here, okay? I'm just doing it because I'm running out of space on this side. But another way is maybe my person is really savvy with a boat. Maybe he wants to go to Thunder Bay and just goes right across this way. So there's 3 possible routes from Winnipeg to Sault Ste. Marie. And then maybe there's 2. And 2 routes from Sault Ste. Marie to London. So for example, from Sault Ste. Marie, you might go like this, down to London. Or maybe you might, I don't know, for some reason go onto the US side and work your way around to get to London. I don't make the rules. My green friend made the rules, okay, of where we're going. That includes a boat. I'm not the savvy type to do that. Okay. But the point is that there's 3 routes from Winnipeg to Sault Ste. Marie, and there's 2 routes from Sault Ste. Marie to London. I want to know how many possible routes are there from Winnipeg to London via Sault Ste. Marie. So let me show you how you could use the multiplication principle. So you can imagine it like you're committing to a choice. I like my example I talked about with the nested loop. Pick a route from Winnipeg to Sault Ste. Marie. There's 3 possibilities here, right? So you pick a route from Winnipeg to Sault Ste. Marie, then you pick a route from Sault Ste. Marie to London, which there are 2 possibilities. Now, do you see that I do this and then I do this, right? Does everybody see that? So notice that I'm going to use the multiplication principle here. And now, how many possible routes are there? How many possible routes are there? Well, it's a piece of cake. If you know the multiplication principle. By the multiplication principle, the number of possible routes is, well, we have 3 possibilities from Winnipeg to Sault Ste. Marie. And then I have 2 possibilities from Sault Ste. Marie to London. So we have 3 times 2, which equals 6. Piece of cake, right? So this is what the multiplication principle is all about. You commit to some choice, and then you commit to another choice. You think of it like a multi-stage process like this. It's very intuitive. In the same sense that, like we talked about, like if I have a nested loop, I commit to a value of I, then I commit to a value of j for like the outermost loop, the innermost loop, then I do something, right? So the number of possibilities is the product of how many possible values that first one will take on, then the second one. Just in the same way that we could talk about, I commit to a choice from Winnipeg to Sault Ste. Marie, and then from Sault Ste. Marie to London. Pretty fun stuff, right? Like our lovely person here can tell us that, I don't know if our lovely green friend did actually go across from Winnipeg to Sault Ste. Marie across the Great Lakes like that. I don't know. I'm not going to ask, okay? Have not a great day. We're going to be nice. So, anyways, now that we've talked about multiplication principle, we've seen how we can apply it. I want to give you some examples of combinatorial objects, because many of them can be counted using the multiplication principle in very clever ways. But I thought it'd be a good idea to show you how you could use the multiplication principle by deriving some of these objects in terms of how many there are. So we're going to consider the following problem. So we're going to talk about selecting from n objects, k of them. So we're going to pick k of the n objects with repeats. So I'm allowed to take the same object multiple times. And you might ask, Dan, if you're taking the object, how do you take it multiple times? You're going to see what I'm talking about here in a moment. So the big thing I really want you to notice about that, so we are given n objects, we're given n objects to choose from. Each selection does not depend on the previous choice. That says the previous choice. So I want you to think about this as a k-step process, seeing as I'm picking k of them. So you imagine I have my objects. So I got my objects. So these are my objects. And I get to choose k of them, but I'm allowed to repeat them, right? So imagine I have k bins. 1, 2, 3, 4, 5, all the way up to k. So I have k bins that I can put a label for an object that exists in here. So what I'm saying is, each one of these positions, it's like me picking one of the n objects, right? But I want to label with an object. And the way you would go about this is you imagine I label bin 1 with any of the objects. So that's the first action. Then, so you label bin 1, so you pick one of these objects, you label that object for this bin. So imagine you take like a sticker, you put it on the front and you say, this is that object's bin, okay? So you can imagine I'm gonna put a sticker on front of each one of these bins that represents one of the objects I'm going to pick for it. So the first action is label bin 1. And keep in mind it could be labeled bin 2, but it doesn't matter in this case because they don't depend on the previous choice. Then you do the same. Then you do this for bins 2, 3, and so on until you get the bin K. You do the same thing. So that, just to reiterate, this says then do this for bins 2, 3, all the way up to K. So notice that you're not worrying about, you could pick any of the objects for labeling the bins. So what does that mean? So how many ways can I label the first bin? Well, I could pick any of the objects, right? There's n of them. How many ways can I label the second bin? Well, there's n of them. How many ways can I label the third bin? Well, there's n of them. And so on. How about labeling bin K? Well, there's n of them. Hence, so the point is that it does not depend on the previous choice. You get to pick from n of the objects every single time, and you pick k of them. Hence, by the multiplication principle, the number of ways to select k objects from n objects with repeats allowed is as follows. Well, we said the first bin, n, many, second bin, n, many, and so on. You do this k times, right? Because there's k bins. Just in the same sense that we talked about. We make k selections. Each one, there's n ways to do it. You have k times, that means that the number of ways is n to the power of k. So remember, this is because the number of choices is n for each action, and we do it k times. That's it. That's it. So very often, a common way this pops up, so a common application of this is where, so there are objects, and any of them may appear in a bin, where you can think of it like a slot, a position. These are all just different ways of saying the same thing. With reuse in some ordering. So you can imagine this like I talked about. You imagine it like a sequence of me labeling each one of the bins with some object. This is just some process I've decided upon. So I look at the way I could potentially do that from labeling 1, 2, 3, all the way up to K. So this could, for example, take on the form of an ordered sequence, or it could even be a plan in a day. So let me give you a couple examples of what I mean by this. So I thought I'd maybe give an example that's more tech related. Let's talk about passwords. By no means am I talking about the effective passwords. I'm just talking about some basic type of information. See, suppose that I wanted to know the number of possible passwords. Number of possible passwords of length k is equal to 6 that consist of lowercase alphabetical letters. So remember, that's 26. There's 26 possibilities here. In English, so I'm just going to make sure it's clear that this is in English, is what? Well, think of it as a process. So imagine you have your first position in the password. So imagine you have 6 positions. 1, 2, 3, 4, 5. So I have 1, 2, 3, 4, 5, 6. So in each one of these positions, what can I put right here? I could put a lowercase a, b, c, d, e, all the way up to z. Any one of those could go in this first spot. So for example, so this would be your first letter. This would be 26 possibilities. Then you have your second letter. Again, 26 possibilities. And so on. So just as an example, I could have A, B, B, A, C, A, right? That's one possible way I could assign the letters. And I want to know how many of these exist. Well, as we've seen, the number of ways of assigning the first position, then the second position, and the third position, each one of these assignments is 26. So if I do it k times, how many are there? When k is 6. Well, it's 26 because I have 26 possibilities for each one of my assignments of a character. And I do it k times. What's k? 6. So it's 26 to the power of 6, which is in fact equal to, and I'm hoping that my calculation here is correct. It's 308,915,776. I'm hoping that calculation is correct. I did it by hand. Now, let's give you another example. So this is what I mean by, you can think of it as an ordered sequence. So this is just an ordered sequence. So in this case, I assign characters to 6 positions. And the ordering of them does matter. Here's another example. If you have a choice, bring it back to thinking about meals. If you have a choice from 2, which we're going to prescribe that this n is equal to 2, from two different types of meals in the day, and the kind of meals you can have in the day are breakfast, lunch. Sorry guys, no brunch everybody. I'm more of a brunch kind of person, but no brunch. We're just gonna have 3 here. You can always change this. Then dinner. In fact, I'll encourage you to think about adding brunch in here. For instance. So we're gonna imagine I have 3 meals in the day. I don't say that you have to, but this is just a basic example. You're always welcome to change what n and k are in the day. Then, question is, how many possible meal plans are there? So I have two different possible choices for the types of meals, and I have 3 meals in a day. So how many possible meal plans are there? How many can there be then? Then the number of possible meal plans is 2 to the power of 3, because each time I'm going to have a meal, again, you can view it just like we had up here. So you have your breakfast, lunch, dinner. You get to choose from meal 1 or meal 2. So you get meal 1 or meal 2 for each one of these. And you do it 3 times. Which in total, 2 cubed is 8. See, it's pretty nice, right? But yeah, that's the multiplication principle, and hoping that this will help you see how we can use the multiplication principle in a variety of different ways. Are there any questions? Any questions at all? It's very quiet today. It's fairly quiet today. We're getting to more of the juicy stuff here soon. Yeah, because after this, we're going to be talking about permutations. So that's actually the next thing we're going to discuss is permutations. And then we're going to talk about combinations after that. But we'll do some exercises around permutations and combinations, just a few. And then we'll see how we can generalize some of our ideas from combinations and come up with a nice little toolkit beyond these more fundamentals. Because oftentimes people ask, Dan, how exactly do I know how to count? And this comes back to something I said at the beginning of today's lecture, is that sometimes it's not trivial how to count. We like to think counting's very easy, but you have to be very careful when you count. And I would like to make sure I have ways of ensuring that I am doing it correctly. And that's really the main point of what we're doing here today. And that's the value of knowing some combinatorics. It's knowing how to count. Especially over discrete objects. That's kind of like the big thing with combinatorics. Let me just erase the boards. I'm going to bring us back over here. I hope everyone's having a beautiful day. Again, if anybody has any questions or anything, don't hesitate to bug me in the chat. Happy to answer any questions. If it's anything too involved, we'll keep it until after, but most certainly we can chat about this. Now we're going to get into actual talking about combinatorial objects, some pretty standard ones. But yeah, the thing we just talked about previously, very handy if you ever, one example I like to give when we start talking about different topics like hash functions or other things of that sort. Sometimes you want to know how many possible keys can there be for, say, for example, a student number. So you get an idea of how many keys are possible versus the ones that you maybe want to be considerate about. You could use just the counting principles we just talked about to compute that. Just as a quick example, while I'm just going to drink a little bit of water, is suppose that you had a student number, and it could be a value that is between 0 up to 9 for each digit. And you have a 9-digit student number. How many possible student numbers can there be? Well, there's 10 choices, right? 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you make how many positions? There's 9, right? So it's 10 to the power of what? 9. So you can see that the first example is just another manifestation of the same thing. Just, you could talk about numeric digits instead. Okay. I don't see any questions, so we're going to proceed. So up to this point, we've talked about the addition principle, we've talked about the multiplication principle, we've talked about some basic counting tricks up to this point. I'm going to start talking about some combinatorial objects, specifically some classic ones for combinatorics, namely permutations and combinations. I'm going to start with permutations. There's at least a couple different breeds of these. So let's talk about permutations. So first I got to describe to you what a permutation is. So for some set of objects or elements. So I must stress that for this definition, it's okay if you consider it a collection. All you have to do equivalently to turn it into a set is just uniquely identify each of your objects by their position, for example. And then now you have a set. It is an ordering of the objects / elements. So this would be in a row, left to right. That's at least how we're going to interpret them here. So let me give you an example. Actually, let me elaborate on this a little bit further. We're not going to be interested in just getting one permutation of a set. We're going to be interested in a listing of all of them. So these are going to be orderings. So I'm going to describe them as ordered tuples or ordered sets. So you can just imagine it as a sequence or a list, for example, of the elements. So the order here does matter. So given a finite and non-empty set A, it is a listing. It's a listing of the elements where each object in a permutation of A has a position or index. As I said, is that you could imagine you have it where you put the first object in position 1, it could be that the second object goes in position 3, and so on. You could describe the permutation in terms of how you assign the objects to positions naturally, because they each have their own position. So it's just a reassigning where they go. This is especially meaningful when you start talking about objects for which, collections of objects and rearranging those, because each one of those will have their own position in that collection. So they imagine them as being ordered by their keys, for example. In fact, if I want to talk about a collection, just imagine I have what we would describe it as what we call a multi-set. So you imagine each one of those has a position. It's very intuitive when you fix the elements to some position. There's some fancy notation around some of this stuff. I'm not going to refer to so much of that here. So the point is that given a finite and non-empty set A, it is a listing of the elements where each object in a permutation of A has a position or index. For example, if I give you a set A with A, B, and C, then there are 6 possible permutations. Now, I haven't told you how you know that, but I'll show you how you get it in a moment. 6 possible permutations of A. So let me list them for you. So first, let's consider the most trivial one. I'm just going to literally write out each one of the elements. I'm going to assign A to be position 1, B to be position 2, and C to be position 3. So notice I'm using rounded parentheses to indicate that there's an ordering. Another one is I could swap A and B, so I get B, A, C. Another one I could do is I could swap, let's try this one. Let's go C, A, B. So I'm just going to imagine I just shifted over C over, and then I get C back over here. So like I right shifted it like this. Naturally, I could take this and I can write it in a somewhat different way by flipping C and B. So I flip those two around, so I get C and B here, like this. Here I'm going to write B, C, and A. And naturally I'm going to have C, B, and A. I think I got them all. Got ABC, BAC, CAB. You don't see any repeats in here, right? There's no duplicates. No duplicate orderings. Here we got CAB, CBA. So notice that this one commits A into the first position. And then it just considers all possible pairings of B and C. This one commits B to the first position, and then it swaps around A and C. Then this one commits the first position to be a C. That's actually how I came up with this listing. This is a nice, easy way to try to list these. As you can imagine, I start off with the first position, I fix that, and then I enumerate from the second position to the third position, and so on. You could do something like that to list these out. The point is you have to exhaust all of them. This number could get quite big. 6 is pretty small for now. So a very natural question is the one I just alluded to. How many permutations are there of set A? Well, now let's think about this in a somewhat different way. Now, remember that it's an ordering, right? It's an ordering, right? And we talked actually about this previously when we talked about the multiplication principle. We actually, in one of our applications, we talked about when we're allowed to reuse elements. So in that case, I was able to have the first position have on, so you can think of it like I was talking about when I enumerated these. When I wrote out my list, I committed to the first position, and then I committed to the second position. Then I commit to the third position. But notice that once I commit one element to the first position, I can't use it again. That's what differs between our previous examples. So let's go back to the multiplication principle and derive a different way of going about this. So we have a process of doing this. So how many permutations are there of set A? Well, to write this down, to write down a permutation, we do the following. And let's head over here. We do the following. Well, first, we choose an element to write first. So we choose an element to write first. So there's n possible elements when I did this. Once I commit to the first position, what did I say? We can't write down that first position's assignment again. So we choose an element to write second, right? We choose an element to write second. Since I've already committed to the first position, there's n minus 1 other elements I can use. And so on. You could do this for the third, right? So choose an element to write third. So I have n minus 2 possibilities. And I can keep doing this until I've made my kth choice. Or in our case, we want to know all the possible listings of n elements. I'll come back to that thing we just said in a moment. So as I have n of them. Because I have to, remember, I want to know how to list all of the elements, all the possible orderings. Since there's n elements in the set, I'm going to do this n times. So we choose an element to write last. And in this case, we force the very last position. That's something that's rather helpful to remember, is that the last position always gets forced. So there's one possibility in this case. So what does the multiplication principle tell us then? We have an n-step process. So I do n steps. I commit to the first position, second, third, and so on. And it doesn't matter if I did this one first or that one. Notice that if I'm talking about, if I make the first choice, I lose an element, right? So when I make this commitment in step 2, every other commitment I make in the future, they don't alter in their quantities, right? They're always going to be n minus 2 many elements left, and so on. So when I make the first choice, it doesn't matter if which letter I do pick or which element I pick from A, like in our previous example. It doesn't matter which one it is, I lose one element I can use. So in step 2, I have n minus 1. It doesn't magically change to anything else. So we can use the multiplication principle. So then, by the multiplication principle, the number of permutations of A equals n times n minus 1 times n minus 2 times all the way times the 2 times 1. And we actually have a very special name for this. So we actually call this quantity that we have here, we call this n factorial, which is written as n with an exclamation mark. So just to be clear, n factorial equals the product from I is equal to 1 to n of I, where we're going to define, or it'll make sense when I explain it to you, hopefully, that 0 factorial is going to be equal to 1. So you're allowed to take on value 0 and above for an integer, and that's how we could define n factorial for counting permutations. There's a very combinatorial meaning, okay? So here's the theorem. The number of permutations of a finite set A with n greater or equal to 1 elements is n factorial. Nice, right? So, for example, I encourage you to try this for, let's try 3 factorial and see if we get 6. Well, we have 3 elements, so it's 3 factorial, which is 3 times 2 times 1. Well, 3 times 2 is 6. 6 times 1 is 6. So just as a quick example, hand calculation, That's how we got the 6 actually over here. That's how we actually got that 6. So now that brings me to talking about something strange that I brought up. I said that 0 factorial is equal to 1. And you might be like, okay, what does that mean? What's that all about? What the heck is a 0 factorial? So sometimes this is a common question of what it means. And there's at least a couple different ways you can derive a reasonable argument for why 0 factorial is equal to 1. I'll give you one such example. So let's talk about the number of arrangements of the empty set. So let's talk about this. So just for context, if you're not sure what the empty set is, it is, as the name suggests, it is a set that has no elements in it. It looks like this. You don't have stuff inside of here? There's nothing in here. This is also written very often like this. So that's what I'm referring to when I talk about the empty set. So when we consider the empty set, how many ways can I list elements of the empty set? How many ways can we list the elements of the empty set? Well, think of it. There are no elements. Now, you might be very tempted to say that there are no orderings because there's no elements. But let me go back one sec. How many orderings are there of this set? How many are there? Well, remember, we are listing the elements of the set. We prescribe a number to each one, but remember, this doesn't have any elements in it. So there's really only one possible listing. There is only one listing. The empty listing. The empty listing. So, you know how we used rounded parentheses? It looks something like this. It would just have no elements in it. That's the only one that exists for the empty set. Hence, the number, I'll say hence, why the number of permutations of a set with no elements is 1, which equals 0 factorial. It's a very natural way of defining 0 factorial. It's because when I have no elements in the set, it simply means that there's only one way you can arrange the elements, namely as just an empty listing. There's only one way of listing that. So this is one reason why 0 factorial is often defined to be equal to 1. It is because of this combinatorial understanding of what that means. So you can also think about this in terms of another combinatorial object called a combination that I won't discuss yet. This is just a fun aside to talk about. So I thought it'd be a good idea I do some examples with you of applying permutations. So I thought one common way you first encounter these types of problems is through arranging words. So I want to know how many ways I can rearrange a word, for example. Maybe not in the most smartest of ways, but nonetheless ways that you may do it. So I'm going to refer to this as mochi time, because all of our little exercises here are going to involve the word mochi. So consider the word mochi, all in capital letters, like this. We're going to go through a variety of scenarios and see how we would go about counting the number of objects for each of the scenarios using what we know up to this point. So the first example we're going to go through is how many ways can the word mochi be arranged? So that also includes mochi itself. So remember that all in this word here, there's something rather important I really want you to take note of, is that each of these letters in this word are actually distinct. Do you see that none of them repeat each other? So equivalent way of reformulating this is as follows. So here's an equivalent question. As the letters are all distinct. The fact that they're distinct matters here. The letters are all distinct. Well, how many permutations are there of the set, or I'm going to put each one of the letters in as an element in my set. I'm going to like to think about these like a letter group, where I might group multiple letters together, but for us, we're going to keep it simple at this stage. Of the set M, with another element being an O, another element being a C, another element being an H, and another element being an I. So I have a set with 5 elements in it. I have a set with 5 elements in it. Oh, my I's a little bit off the side. Let's bring that in a little bit. H, I. My apologies. How many permutations are there of the set with these 5 elements in it? Well, it has 5 elements, and remember the reason why this is an equivalent question is because I want to know how to rearrange the letters of the word mochi. All those letters are distinct. They all are distinct elements of a set, right? There are no duplicates. So it means that when I rearrange these terms, the ordering is what I care about. The number of times I can I can arrange mochi. The same way as how many times can I assign an ordering to the elements in that set. So since there are 5 symbols, the total number of ways where the word mochi can be arranged is 5 factorial, right? Which that's 5 times 4 times 3 times 2 times 1. You might ask, Dan, how do you calculate this off the top of your head? Well, think about it. 5 times 4, that's 20, right? 3 times 2, that's 6. So I have 20 times 6. Well, 5 times 6 is 20 times 5 is 100, right? So 6 times 5 would be 120. And that's just multiplied by 1, so it's 120. There's 120. That's pretty cute, right? Let's do another example. Now, do you take note of how I organized my thoughts here? Now, you can think about this in several different ways, but this is one common way. Is you try to think about, okay, all these letters are distinct. I have to assign an ordering to them. I have 5 of these. Now, I want you to think about like letter groups for this next example. Example. How many ways? So we're going to just think about, if we have the word mochi, how many ways if M and O must be together. So I want to know how many ways you can arrange the word mochi if M-O, these 2 letters must be together in the string. Well, let's just apply the exact same principles. All my elements are distinct, right? M-O is distinct from C, is distinct from H, distinct from I, right? But here's the thing. I want M and O to be together. What can I do? What can I do? It's really nice and easy. You just apply the same principle we did right here, right? Same exact principle. We use the same principle. Notice that I put each letter as a letter group in the set. How many did I have there? I had 5. Well, I can do the same thing here. So you treat the elements as letter groups, i.e. you have MO as one element. You have another letter group that's a C, another letter group that's an H, and another letter group that is an I. So you can use the exact same setup now. So how many elements are in this set? There's not 5 anymore, now there's 4. There's 4 elements in the set. So now we just ask the same question. So, as there are 4, I got 1, 2, 3, 4, right? I have 4 letter groups in the set. The number of ways of arranging the word mochi, where M and O are together, is 4 factorial, right? There's 4 elements in that set. It's 4 times 3 times 2 times 1. Okay. So we got 4 times 3 is 12. 4 times 3 is 12. Times 2 is 24. Times 1, still 24. So that's our second example. I'll just call this 2. Let's get another one in here. Let's do one where we have to actually, we have to fix a position for something in the string. So here's our third example. How many ways can we arrange the word mochi where every arrangement starts with M and ends with what? Let's make it end with I. So now we're considering the scenario where I want to know all possible ways that you can arrange the word mochi, but M has to be the first letter, I has to be the last letter. So let's pick up the same principles that we did over here and think about it. Our arrangements will look something like this. It always will have this form where I commit one to go here, another one to go here, and another one to go here. What are those other ones? What are going in here? What are going in these spots? Most certainly not M or I, right? What can go in these spots without repeating themselves? Well, O, C, and H, right? Do you see very quickly how we're going to answer this? So really, what matters when we're trying to find all the permutations is that, really, right? It's the number of permutations of this set. Because once you've determined one permutation of this set, you just tack on M and I at the start and end respectively, correct? So we have 3 letter groups. O, C, and H. Hence, the number of ways to arrange mochi as described is 3 factorial, right? Because it's a set with 3 elements in it, which is 3 times 2 times 1, which equals 6. Now you might ask, Dan, how do you know, like, did you like double check that? Do I need to make sure? Well, if you're not sure about it, I encourage you to enumerate them all. Or just generate all of them. So, for example, there should be 6 of them. So, most certainly I should be able to do this. Well, let's try to put them all through. So watch. I'm just going to fill the blanks now. Got mochi, right? I can always flip this in reverse. I got H, C, O. I'm going to now swap C and O. So I got C, O, H. I'm going to flip and reverse that, so I get H, O, C. And then I'm going to do the similar thing that I did actually in my first example with permutation. This actually should remind you of the very first example we did of me showing you the list of all the permutations. So all my listings. So these are all 6 possibilities, just like we talked about before. So this is just to confirm the count that we got. So there's 6 listings here, 6 permutations, and we're done. So that's all I have to really say about permutations. But now we're going to go back and revisit how we derived the number of permutations of a set. Now, previously we talked about this idea of having it where we pick the elements, but we can reuse them. What if I was not able to reuse them when I pick k objects from a set of n objects? This brings me to the concept of a k-permutation. So let's talk about a k-permutation. So now we're going to talk about k-permutation. So let me define what that is. I don't need to be as sophisticated about this. So suppose we wish to consider some some ordering of k elements without repeats. So you're not allowed to reuse the elements. We've previously seen what we could do with repeats when we talked about the multiplication principle. So from a set of n elements, such an arrangement is called a k-permutation. Specifically, it's a k-permutation of that set. So just to give you an example of what I'm talking about here, let me just get a different marker. Okay, we'll go with this one. So suppose that I choose no, let's do the example here. So for example, if A is going to be the set A, B, and C, so I have three elements in here, namely A, B, and C. I deliberately chose this example so that way you can compare it against some of the other definitions that we had. It has n is equal to 3 elements, right? And for each 0 is less or equal to k is less than or equal to n, we can list them. So I'm going to go through each value possible of k and see what we get, okay? Just going to flick this marker off. It's gone. It's gone. That was quite dramatic. So if I consider k is equal to 0, well, how many orderings are there if I pick no elements? Well, there's just one that exists, right? The empty listing. So it's only the empty listing because I didn't pick any. If I pick k as 1, there are 3, right? Namely, you've got A, B, C, each in their own listing, just by themselves like that. How about k is equal to 2? So there are 6 in this case. We're going to have AB, we're going to have BA, we're going to have CA, then we're going to have, we'll have AC, then we'll have BC, then we'll have CB. So notice that it is just simply, if I pick 2 of the elements, I want to know all the possible ways I can order them. So in this case, you can imagine I pick the first one, and then I pick a second one, right? It should ring a bell with something we talked about when we derived the number of permutations. It's a very similar process. It's just that we're not going to go all the way and select all n. So you could do this again. Now let's suppose that we consider the case when we have 3, which happens to be n in this case. So again, there are 6. We have A, B, and C. We have B, A, C. We have C, A, B. We have C, we have C, A, B. We have A, B, C. We have, C, A, B. Whichever ones do we got? We got A, C, B. I'll tell you up front that this is actually a fairly easy example. We have CBA. Why do I say that? I said this actually previously, or at least a little earlier, is that once you consider the last position, what did I say previously? It forces the last position. So do you notice right away that all I did was just tack on the last element on each one of these? So, for example, when I want to get the last position, like we did when we computed n factorial, when I chose n elements, this is when we get k as n. So it means that we only have one choice at the end. So we immediately know what the final position is going to occupy for what element that is, right? We know what the last element's always going to be. That's why this should be no coincidence that these are the exact same numbers. So, anyways, let's talk about how we derive the number of k permutations of a set with n elements. So hopefully the definition is clear to everybody. So remember, the big idea here is I imagine I'm going through and fixing a position for each one of the elements that go in the ordering. I give each one a position, but I'm only allowed to pick k of them. So let's go back to what we did before. Like before, for permutations, for perms, we can derive using the multiplication principle, the number of k-permutations of a set of n elements. As we simply pick k of the n objects, right? So you can almost look at this like a special version of what we just argued before when we came up with the number of permutations of a set A. So what you did was we select a first element, right? That's what we did last time, which had n choices, or n possibilities. Then we pick a second one, right? We're just setting it up like a series of choices. We're committing to each one of the positions. Like the second element, how many can I do? N minus 1, there's n minus 1 choices this time. And we can keep doing this until we've selected k many, right? So select the kth element. Now we have to be a bit careful about this. Okay, so it's going to be that there's n. So how do I get the pick in total if I were trying to enumerate all of the permutations of a set? I get n of them, right? But I'm picking k. But remember, k could potentially be 0, right? So imagine if I picked none, right? Well, it has to still be true, right? It still has to be that it gives me the correct count like we had over here. Well, we have n minus k minus 1. Many possible choices, which is n minus k plus 1 choices. If you're wondering why it's k minus 1, it's because remember that when we start our counting, we're starting at 1 in this list, so it's somewhat deceptive. So keep that in mind. So just as a quick example of what I mean by this, you can imagine Because remember, we're also starting from the back end, right? So you can imagine if I were to pick, say if I only picked one element, then k would be 1, so it's 1 minus 1, which is 0. Then I would have n choices, just like I have here. If I have 2, then I would have, how many? I would have n minus 1 choices, right? So please don't let this k minus 1 throw you off. That's because of the way we're indexing when we make the choices. Because we're starting, when I write this out like this, we're actually starting from the bottom and we're subtracting up the correct number of elements to the appropriate spot in our list. Because you got to remember, we count downwards the higher the number gets. So you can imagine this in the case for which you select n elements. This would be n minus 1. So this would just end up being one choice, right? Because we left with one choice. We notice that's why. So hopefully that is clear where this k minus 1 comes from. It's just the way we listed them. It's about the way we list them. I just need to make sure that we're keeping the appropriate count of choices. So now we can use the multiplication principle. So by the multiplication principle, this number is as follows. It's n times n minus 1 times n minus 2 times all the way to n minus k plus 1, which this is equal to n factorial over n minus k factorial. Now you might ask, where did this come from? Well, remember, when you write this out, you have all of these terms. Notice that if I divide, so if I write that out, I divide by n minus k factorial, I take out all of the useless terms, the ones that we never end up using from n factorial, and we get that. This is just one way of writing this down. Very often, this right here gets written in a specific way. So this is often written as, so this is denoted as PNK. So this is the number of k permutations of n objects. So P and K there, that equals n factorial over n minus k factorial, or equivalently this. Pretty nice, right? So let's do a couple of examples of applying this, just to see what we can use this potentially for. And keep in mind, it doesn't have to be about using things. I find a very common mistake people make is that they get obsessed with that it has to be used. It can't just be studied on its own regard. It's a feature that we can use it for things. Okay, let's do a couple of examples. So how many ways can 3 of the letters of the word cake, or cakes, let's go cakes, of the word cakes, be selected and written in a row? So how many ways can 3 of the letters of the word cakes, which I must note has 5 letters, be selected and written in a row? Well, take note, akin to some of the previous examples we did, all the letters in this are distinct. So we have 5 distinct letters. We have 5 distinct letters. Each can be considered its own letter group, as we discussed previously. Letter group. So that means that we end up with a set that looks like this. So you can imagine it just like we were given a set like this. And we select 3 of them. But what is that? What is that, everybody? What is this? It's just determining the number of 3 permutations of this set. This is just the 3 permutations of this set. And in total, the number of these are as follows. Okay, I have 5 elements. I choose 3 of them, right? So what is that? So there's a feature of this notation that's rather helpful. When you talk about P and K, remember N is the number of elements, K is the number of elements you get to pick from. So I get to pick 3 of them. So very naturally I have P 5, 3. So that's 5 factorial over 5 minus 3 factorial, which this is 5 times 4 times 3 times 2 factorial. Usually the trick is you write it out until one of the largest factorials of the denominator appears. Then you can cancel them over 2 factorial, because 5 minus 3 is 2. So I have 2 factorial, this 2 factorial, and that 2 factorial go say bye-bye to each other. So I end up with 5 times 4 times 3, which equals 60. Because 5 times 4 is 20, multiplied by 3, that's 60. So now I want to do something similar to the above scenario. So hopefully that is clear, everybody, where I got 60 from. I want to do a very similar scenario. Now, let's think about this. So consider the same scenario above. But the last letter must be K, the capital K. It has to be K this time for the last letter. This should remind you of one of the previous examples we did, except we have to be careful here, right? So remember that I want to know how many ways you can have 3 of the letters written up, selected and written in a row, but the last position now is going to be fixed as a K. So what can go, so notice I have 2 other spots available, so I'm actually choosing 2 letters to go in this sequence. Which letters though? Because K is already being used, right? So I'm choosing from this set. I get to pick C, A, E, or S, akin to our previous example here. Notice K isn't there. We have C, A, E, and S. Let me just write that A a little bit more carefully. But what is this? So this is for the remaining positions. But what is that? What I'm asking is actually an equivalent question, akin to our example previously where we talked about mochi with the first letter and last letter being fixed. I just need to know the number of 2 permutations of that set, the one without the k in it. But what kind of permutations? I need 2 permutations of that set, correct? I'm pretty sure that's what I just said, but I just want to make sure it's clear. So let's clarify this. So this is just the number of ways is the number of 2 permutations of this set, CAES, which how many elements does CAES have? It has 4 elements in it. It has 4. So this is going to end up being P42, which equals 4 factorial over 4 minus 2 factorial, which equals 4 times 3 times 2 factorial. Then I end up with my then I have another 2 factorial. These two are going to cancel. So I end up with 4 times 3, which is equal to 12. Piece of cake, right? That's all I have to say about permutations, at least at this stage. Are there any questions? Any questions at all? Don't be shy. It's been a fairly quiet day. I know that combinatorics can be a little bit of a hit or miss with some people. So now that we've talked about permutations, the natural cousin of this is combinations. Because in permutations, we care about the ordering. So we're trying to determine orderings of elements that I pick from. In combinations, I don't care about I don't care the ordering they take on. I just care about what's in my selection. So the ordering doesn't matter. It's actually it's what's in the thing. Just like if I'm going to the grocery store, I don't care what order I pick up the cheese. I just care that I have the cheeses. In permutations, I would care about the order in which I do that. In combinations, I'll just care about having the cheese. Like if I'm looking for a mozzarella, a cheddar, and I don't know, a Gouda, if I was considering the number of ways I could select these 3 types of cheeses, that's one way of doing it. That's more of the permutation way of going about things. The combination way is just saying, I just want to know that you got me each one of the cheeses, okay, Dan? And yes, this isn't actually a story that actually happened. It's just a figurative example. So let's head over here. We're going to talk about combinations next. Just going to move this over here. Okay. Seeing whereabouts we are. Oh yeah, we're getting some good stuff. I've been looking forward to teaching you guys this, or at least showing you this idea that I was thinking about the other day. Okay, previously we've talked about the addition principle and the multiplication principle. We talked about factorial, we've talked about permutations, we talked about k-permutations. Now I'm going to show you the cousin of permutations, combinations. Namely, we're going to start off with talking about k-combinations. So we're going to talk about k-combinations first. So k-combination of a set. So we're going to let n and k be positive integers or potentially 0. So this is a fancy way of me saying, oh, positive integer or 0. That's a union in there where k is less than or equal to n. a k combination, of a set A I'll say finite set A of n elements is a subset. So it means it's if I were to look in my set, I take some of the elements and I put them aside. That's a subset. It could be even all of them, or maybe even none of them. Is a subset with k of the n elements. So a k combination would be some subset that is of size k, where it's k of the elements of the set A that consists of n elements. So let's do an example. Let's consider the example we've been using. Suppose that we're given a set A, which has elements A, B, and C in it, which has n is equal to 3, right? Because there's 3 elements in it. And for each 0 is less than or equal to k is less than or equal to n, we have as follows. So I'm going to show you how you would list out each one of these. So if you want to know what a k combination would be for a given k, it'd be somewhere in this listing of subsets. Just to be clear, they're subsets now. Now we do not care about the ordering. This is the one thing that's going to really separate permutations from combinations. Is like I talked about on side, I talked about the idea that suppose I go to the grocery store and I'm looking for some cheese. I want to get mozzarella, cheddar, and Gouda. In the world of permutations, I would care about which order I did receive those types of cheeses. In the combinations world, I would just care about that you got me the cheeses I was after. So I don't care about the order they appear in. It's just that they appear in that subset. So the order does not matter. So I'll just mention this off to the side. That's different from permutations. Order does not matter. So when k is 0, there's namely only one subset that you don't pick any elements from. It's namely the empty set. This is kind of like the parallel version of our permutations where we had the empty listing. So it's just 1. When k is 1, there are 3 k combinations, namely where you put one element each in a subset. So I have A, B, and C. These are 3 different subsets of A, each with one element in it. So I get to choose one element. How about 2? For 2, I can have AB together. I can have AC together, or I can have BC, right? So please take note that if I put CB, that's the exact same subset. Remember, in a set, we don't care about the order the elements are in. Then for k is equal to 3, this is when we have n, we have just A, B, and C. So please take note, the order does not matter. One interesting detail I am not going to go into in this discussion, but one thing I really want to point out to you is that there is a little bit of there is a symmetry from the smallest value of k to the largest value of k. Do you take note of that? It's very interesting. That is not a coincidence. That is actually a very special property that, should we explore more about combinations and how they operate for counts in relation to each other, we might explore this property in the future. So, the first thing I really want to point out to you, this is just a fun observation that I really want you to notice. It's just something I like to point out so you can pick it up and then put it back behind your ear as a piece of something to help you think about things in other ways in the future. Notice that all possible subsets of A are listed over here, right? So all the possible ways I can grab those elements and throw them in some bucket including when I don't pick any, or if I take all of them, they're all in here. These are all the possible subsets of A. So if I go over each value of k over this range, and I determine the k combinations for each k, I end up with every possible subset of A. But if you take all of these and you perform a union operation on each one of these buckets, suppose if I listed out all of these, and I take all of them, I throw them into one super bucket. This actually is what we call, so I'll say taken together. It forms the power set of A. The power set of A. That's just a fun aside. So just to be clear, the power set in this case would be the empty set, A, B, C, A, B, A, C, B, C. We got B, C, and then we have A, B, C. Right, I got 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. Okay, good. So this would be the power set of that set A. So I'm getting very, very excited. It's also not a coincidence that that number looks like a power of, like if you count up how many elements are in the power set, it looks like a power of 2. It looks quite similar to a power of 2. That's not a coincidence either. So I got 1, 2, 3, 4, 5, 6, 7, 8, right? That shouldn't be very surprising if you think a little bit carefully about it, but I'll let you think about that, why this might look like a power of 2 of some kind, why it looks somewhat symmetric. These are all interesting combinatorial properties of these objects. So that is something we'll most certainly explore in the future if somebody is interested in this. So anyways, a very natural question, as we have been exploring so far in our discussion about combinatorics here, is how many k combinations that are there of a given set? So let's answer this question. So I've been really excited to talk to you about this. How many k combinations are there? So we're going to explore this now. I'm going to do another example that illustrates some of the things that are going on, so that hopefully you can be exposed to something that's relating k combinations with k permutations, because there's actually a close relationship between these two types of objects. A very close relationship. And in fact, how we're going to derive this answer. So let's revisit k permutations. Here, I'll say revisit k permutations. Here we select k elements from n elements. But we care about, I'll put that in quotation marks, we care about what is an intrinsic property of k permutations, is that these are orderings. The order of the choices. So when the element appears, we care about that. We care about it. We care about it when we talk about our k permutations, right? Any one of these k permutations, it's some ordering. That's the point I'm getting at. In k combinations, we care about whether an element appears or not. Right? That's all we really care about with the K combination, is we just care if the element appears or it doesn't appear. It's either going to appear or it doesn't appear, right? So let's do an example. I just really want to show you something rather. Just something I was just on top of my head. I was thinking this is fun. So as an example, let's consider this set: 1, 3, 5, and 7. All its 3 permutations are the following. So let me list them all out for you. So I got 1, 3, 5, 1, 3, 7, 1, 5, 7, 3, 5, 7. Then I'm going to now, let's write the next row, 1, 5, 3. And I must stress there's going to be something very special about how I list these. So please, while you're writing this down, please take note of how I'm doing it. So it might give you a hint of what I'm up to. I'm going to show you what I'm up to in a moment. So I have 1, 5, 3. The next row will have 3, 1, 5. And then I'm going to have 3, 5, 1. Then I'm going to have 5, 1, 3. And then lastly, I'm going to have 5, 3, 1. Second column, 1, 7, 3. So I'm just going to flip 3 and 7. Then I'm going to put 3 in the first spot. 3, 1, 7. Then I have 3, 7, 1. Then I'll put 7 in the first position. 7, 1, 3. Then I have 7, 3, 1. Next, let's do this next column. So I'm going to flip 5 and 7 to make 1, 7, 5. Then we have 5, 1, 7. Then I have 5, 7, 1. And then I'm going to put 7 in the front. 7, 7, 1, 5. And then finally, we're going to have 7, 5, 1. Final column. We have 3, 7, 5. I'm just swapping 5 and 7. Next, I'm going to put 5 into the lead. 5, 3, 7. Then I have 5, 7, 3. Then I'm going to put 7 in the leading position. I'm going to have 7, 3, 5. And then I'm going to have 7, 5, 3. I'll leave it to you as an exercise to double check that I've enumerated all 3 permutations of this set A. So there's something really fascinating going on with the way I've arranged this here. So this is arranged very specially. Does anybody see anything interesting going on over here? So this is a special arrangement that I've cooked up here for you. And in it is actually hiding the multiplication principle in the way I did it. So does anybody see anything fascinating going on here? So if I wanted the answer to how many K combinations there are, what are the K combinations of this set? Particularly, what are the 3 combinations of this set? Well, I pick 3 elements from this set. Remember, I don't care about what origin. You can imagine. Each one of these ones I have on the top of each, in this first row, as a representative of the 3 combination for its respective 3 permutation. So notice that each column actually represents a 3 combination. And all of the 3 combinations, there's actually exactly how many? There's 4 of them. One for each column. And the elements in there are You could take any of the 3 elements from any one of these in this column, and that's the first K combination, well, 3 combination. This is, so you can just look at the top of these, any one of these ones, in one of each column. If you just pluck one of them off from one of the columns, it gives you one of the 3 combinations that are possible. So think about it like this. I want to know how many there are. And let me kind of make this a little bit more evident for you. I'm going to take you back to something cute about geometry. So I have a question for you. How many columns do I have? In this example, I have 4. But I really want to know how I get 4. Now, I want you to imagine that these are actually squares. So imagine I have rows, which are going to represent, this is going to be this is the number of rows, which is the width. And then we have the number of columns. So this is the length. But what is if you think about this as a rectangle, if you're looking for the area, what would the area be of this rectangle? What is the area of this rectangle? If it is, the width is the number of rows and the length is the number of columns. What is it? What exactly is the area of this rectangle? What's the quantity? If these are all units in size, right? We're talking about the number of rows, number of columns. What's the area? Well, what did I enumerate? I enumerated all the 3 permutations. So that area of the rectangle is actually equal to the number of K combinations that are present in my table, which happens to be my listing. Does everybody see that? Pretty fascinating stuff, right? So now you might ask, Dan, how did you come up with this listing, and how do I determine the missing side? Well, I can encourage you to think about how you derive the missing side from all the information we laid out, but I'm going to do it now directly using the what principle? The multiplication principle. So all we have to do is determine this. So what is that? But I want to show you now how I came up with that listing. And you'll see that it actually is just the multiplication principle. So if you're very geometric, if you like to think geometrically about things, you can figure out the answer to this question from the information we just discussed. But I want to be somewhat more formal about this. Just slightly more, just slightly, because I want to show you how you use the multiplication principle here. Okay. In other words, suppose we had a set L with all K combinations of set A. Just generally, because we're not talking about 3 combinations anymore. We're just going to talk about K combinations of set A, where the size of L, or cardinality of L, is the number of elements. In this case, this would be subsets. So these are subsets, the K combinations. So I'll say elements in L. So I want you to notice something. Notice that the k-permutations of A is where we take each k combination in L and compute for each its permutations. Right? We compute all the permutations of that k combination. So notice that all it is actually a process as follows. Is I pick a k combination, then I compute the permutations of that. So that is, we choose a k combination of A. Then, to be more precise than I was, then choose some ordering. Some ordering for the k combination, which makes it into a, what kind of thing? A k permutation. So notice it's actually a process. It's two steps. Well, just remember observations. The number of k permutations in total is n factorial over n minus k factorial, correct? We derived this earlier, which, remember, this we write as p and k, this whole expression. 2, how many permutations are there of k objects? Just k factorial, right? Because remember, when I pick a k combination, that's just some set. I want to know the number of permutations of k elements. It's k factorial. So that will give us the key ingredients for what we need to do. So now do you see how I came up with this table I had over here? Do you see now? So all I did was I choose some k combination. That's a column. Then each row is me selecting some ordering for it. So all I did was I exhausted all of those selections for the first step, and then I exhausted all the selections for the second step. And that's actually how I made that table over there. So that's actually where it comes from. So now, in a beautiful fashion, we can use the multiplication principle. So by the multiplication principle, the size of L times k factorial, right? Because that's what it says. The first step, remember, the first step is that we choose a k combination. That's the size of L. That's how many ways we could pick that, right? Then we choose some ordering for it, which we know that the number of permutations is this. Remember, this right here is step 1. So this is action 1. Then we choose some ordering for the k combination. That's action 2. The first something and the second something. The first something, how many ways can I do that? Well, it's the number of k combinations, which that's what we denoted as L, is the set of all of those. Then I have k factorial. That is the number of ways you could select an ordering for the k or k combination. But what did we determine? Well, when you do this, as I said, once you assign an ordering to a k combination, that is a k permutation. That means that we're actually exhausting all the number of k permutations. So that's actually equal to pnk. Right? But we can simplify this a little further. This is n factorial over n minus k factorial. Now, akin to when we talked about the area of this rectangle, I could divide both sides by what? K factorial. And then I end up with L, the size of L, on one side of this equation. And this is totally valid to do because our numbers always remain positive, right? It never is going to become 0. So I have now that the number of k combinations is equal to n factorial over k factorial times n minus k factorial. So I divided both sides of this equation by k factorial. And now we actually have something interesting going on here, because now we actually know how many k combinations there are. So this right here is the number of k combinations. And it's denoted like this. So this is often read as n choose k. Specifically, n choose k is now going to be equal to n factorial over k factorial times n minus k factorial. So this is read as n choose k. And some people refer to it as the choose function. Some also refer to it as something called the binomial coefficient, which I'm not going to be discussing here today, but it is a close relationship with this so-called choose function. Now, but yeah, no, this is how we can find out this is one way to derive how many k combinations there are of a set A. Pretty fascinating stuff, right? Let's do some examples. So notice that really the relationship between k permutations and k combinations is actually very close. Namely, it's just assigning and ordering to a k combination gives you a k permutation. So let's consider a couple of examples of using our understanding of k combinations. So imagine you have a team of 12 people. Let's not have a team. Let's have a group of 12 people. A group of 12 people to join a team of 5 people. Five people. How many possible teams? How many possible teams of 5 people can you have? Well, we have 12 people we could choose from, but we need to choose 5 of them for the team. Quite naturally. So what we do is we choose 5 people from 12, which is, because remember, we don't care about the order in which we pick them, right? So it means that we're talking about combinations, not permutations. We just care that we pick the people, not what order we pick them in. So we got 12, choose 5, which this is 12 factorial over 5 factorial times 12 minus 5 factorial. But what's this? Oh, this is 12 times 11. So I'm going to show you that, yeah, a common trick is you just write out the factorial as long as you need it till you can cancel one of the terms in the denominator. 10 times 9 times 8 times 7 factorial. So I just write it up to where I get to the factorial there. It's a common trick. And I have 5 factorial times 7 factorial, right? Because 12 minus 5 is 7. So naturally, let's do some canceling. So 7. Naturally as well, we should be able to get rid of some more stuff. Namely, we got 5. So I have 5 times 4 times 3 times 2 times 1. So I got 5 times 4. Okay. I got 5. Okay, we got 5, 4, 3, and we have 2. 1 doesn't really matter, right? So 5 times 2 is 10, right? And 4 times 3 is 12, correct? So we can actually just get rid of 5 factorial entirely if we eliminate 12 by canceling and 10. So we end up with 11 times 9 times 8, which this, I believe this should be correct. It should be 792. So I encourage you to check that calculation. Pretty nifty, right? So next, let's do another example. A very common case where you might run into this scenario is if you're encountering strings, especially if we're talking about computer science. So we've already seen an example where we try to place things in a sequence, such as with passwords when we were talking for a while back. So suppose we are given a bit string. So a bit string, to be clear, consists of zeros and ones. It's written in binary. So it consists of zeros and ones. So let's ask a question about based on how many bits I'm going to use. So a bit is just either a 0 or 1. So how many 8-bit strings? So I must stress that that is going to be a byte, because we have 8 bits. How many 8-bit strings have exactly 5 ones? I'll write 5 in full. I should be doing that anyways. 5 ones in it. Wow. Let's think about this. Okay, I have an 8-bit string. So that means I have 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positions. Each one of them has a unique index, right? This is position 1. You could start at 0 if you wanted to. It doesn't matter. The point is that I have 8 positions. 8 of them. 1, 2, 3, 4, 5, 6, 7, 8. I have 8 positions. So there are 8 positions. And the thing is, there's supposed to be exactly 5 ones in the string. Let's think about, so instead of thinking of it like, oh, well, this position could have a 1 or a 0 in it. This could have a 1 or a 0. This could have a 1 or a 0. Instead, what happens is you pick 5 positions. What do you know about the other positions? If you put a 1 in 5 of the positions, it means all the other ones are going to have zeros in them, correct? So pick 5 positions, and all the rest have zeros. But the thing is, we're making choices based on the set of positions. So this is why I really want to show this example, is sometimes it doesn't look like that we're really making a choice here, but it just really is thinking a little bit more carefully about what are we choosing over. In this case, it's not just a team, it is actually the positions in the string. So carefully conceiving what exactly you're counting over is actually a key element for some cases like this. This is a very helpful example in that regard. So we have a set of positions, capital P. Just gonna have 1, 2, 3, 4, 5, 6, 7, 8. For which we select 5 elements from P, right? 5 elements in P correspond to 5 positions in the string. Those are going to occupy ones. Which has the total possible count of what is it? What's going to go in my choose here? So what are my choices? I'm going to have 8 positions, so I have 8. Choose what? 5. 8 choose 5. 8 factorial over 5 factorial times 8 minus 5 factorial, which this is 8 times 7 times 6 times 5 factorial. And I have a 5 factorial that I'm going to attempt to cancel with. And then I have the 3 factorial, which fortunately I also can cancel out quite nicely. So the 5 factorial could go out with this 5 factorial. And then I have, what else? Well, 6 right here is just 2 times 3, right? Which is the same as 2 times 3 times 1. Which that is just simply 3 factorial. So I end up with 8 times 7, which that is exactly 56. Completing our example. So if somebody asks you, how many 8-bit strings have exactly 5 ones in them? The answer is 56. So that's all I have to say about k-combinations specifically. There's other kinds that we're going to be discussing here shortly. So, are there any questions? Sorry, just getting something to drink. So we're moving into our kind of last section of this. But if any questions, please don't be shy to ask questions. I know this topic can be a little confusing sometimes, but I'm hoping I'm making it pretty clear. Just going to erase the board here. So the last thing we're actually going to discuss here is actually how we talk about k-combinations, but we allow repeated elements. So before we didn't care, okay, we've talked about repeating elements for permutations in another indirect way. But we didn't talk about repeating elements for a combination. So that means that that I would like to know, like, say if I'm allowed to reuse the elements, how many k-combinations are there? So we call these k-combinations with repeats or repetitions. So that's what we're going to focus on here as the last thing we're going to talk about here today. Okay? Yeah, no, we're kind of approaching the end of today's lesson. We're just about there. Just about there. Right now we're just puppy sitting. one of our family friends, family dogs. Hopefully she's doing okay. Hello. Hi, puppy. Puppy. Just looking at me like, what the heck are you talking about? What do you need to do? I just got a dog like staring at me like this, like, what are you up to? Okay. Well, let's since there aren't any questions, like I said, it's a fairly quiet day here. Let's talk about our last thing for today. So previously we talked about k-combinations, namely how we can determine how many k-combinations there are of a set. Remember that this is where we don't care about the order elements appear. We just care about if an element appears or doesn't. So we're trying to find out how many subsets of a set contain of a certain size k. So here, in that case, we did not allow there to be repeated elements. Now I want to talk about if we introduce the ability to include repeating elements. So now we're going to talk about k-combinations with repeats or repetitions. So k-combinations with repeats. Or repetitions. So we're going to be talking about k-combinations with repeats or repetitions. Remember, as I just previously stated, in permutations, we care about the order they are in. In combinations, we do not care about what order the elements appear because we're considering subsets of a given set of size k. Now, in the case of k-combinations, we forbid repeated elements. Now we're going to see what happens if we allow that to be the case. So consider k-combinations where we may reuse elements. Now we're going to need a somewhat different object to represent these things because a set isn't just simply, remember, sets don't contain duplicates, right? So what are we going to use to represent this? Is we're going to use something called a multi-set. So we represent each such selections as a multi-set. So a multi-set is just simply a set where you're allowed to include duplicates, and we count the duplicates. So I write it slightly differently first, just to keep it clear. We're going to use square brackets as opposed to curly brackets. So we're going to use these, not those, because these indicate that there are no duplicates allowed. This one allows duplicates. Now, I want to answer a question, is if I'm allowed, and keep in mind, I'm going to show you some examples, but one question I really want to address is how many k-combinations with repeats are there for a set A? So the way I express these is using a multi-set. So each listing is going to be a multi-set. So one way I can view this, so I'm going to view this in a somewhat different way. So we're going to view the elements of A as buckets to place objects. One for each in A. And then we pick k elements. We pick k elements of A to go into the buckets, right? Because remember, we don't care about the order. We just care that it appears or it doesn't appear. So if I choose 2 of the first element, I want to make sure that that is clearly evident to go into the buckets. And we choose these, right? Yes, Miss Kitty, I know. We're going to choose them, right? That's something that's really important for us, Miss Kitty. So, just as an example, I'm just going to show you what all of the k combinations would look like with repeats for the following set. Suppose I have the set A. We're going to look at the 3 combinations with repeats of this set. A, B, C, D. All the 3 combinations with repeats. And I must stress the repeats part is important. Are. So I could pick the set, I could pick the element A 3 times. So this is how I would write the multi-set. So I have 3 A's. Then I could have A, B. So I pick A twice, and then B once, and C no times, and D no times. I could have A, C. I pick A 2 times, C once, no B's, no D's. A, D. Then I have A, B, B. So I'm going to try 2 B's. Yes, Miss Kitty. I know about that one. I know about that one. I'm getting to it, Miss Kitty. I'm getting to it. It's coming on the board. Yes, yes. So I have A, B, B. Then we have A, B, C. Then we have A, B, D. Then we have A, C, C. So notice that the game in town now is I pick 3 elements, but I'm allowed to reuse them. So just to be very clear, like I could make all of them the same element if I wanted to. So I have A, C, C. I have A, C, D. And I think I have A, D, D. So these are all the ones that start with the letter A in the first position. Now let's consider the ones with B in the leading spot. So I have B, B, B. So I can pick all of them to be B. No A's, no C's, no D's. Then I have B, B, C. Then I have B, B, D. I have B, C, C. I have B, C, D. I have B, D, D. So those are all the ones that start with a B. You could double check these. I encourage you to do so as an exercise. I have C, C, C. C, C, D. And then I have C, D, D. Then next, and finally, we have all D's. D, D, and D. There should be 20 here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So there's 20 possible. 20 possible 3 combinations with repeats of A. So remember, the order does not matter. It is what's in there. But now we're allowed to have repetition. Now, to make this easier for us to think about, now remember, I talked about it like you have a certain number of A's, I have a certain number of B's, a certain number of C's, and a certain number of D's. And I can think of them like placing the elements in buckets. Now, I need a very natural way of talking about one bucket versus another bucket. So I could break them into the different buckets and talk about the different bins and how many are in there. So a very standard way in combinatorics is to go back to our friend, the string, and represent it as a string instead. So let's represent the buckets as lines. So these are bars, actually. I should call them lines or bars. So that's a bar or a line. And and elements in a bucket as a dot. So just as a quick example of what I mean, if I look at A, B, and C, where's A, B, C? Oh, it's right here. A, B, C, a way I could represent this is as follows. So I could put a dot, line, dot, line, dot, line, and that's it. So notice that this says that there's 1 in 1 of A. So there's 1A. This says there's 1 of B, 1 of C, and then this says there's 0 D's, right? So you could conceivably, well, you should be able to find for any one of these multisets, you could build a string like this of just lines or bars and dots. That's it. So you're breaking each one of the buckets. I need some way of representing the buckets. So these separators are being used to represent the separation between my different buckets. So just another example, just to illustrate the point. Let's look for let's go BCC. Where's BCC? Ah, there's BCC. Let's go with this one. So, for example, there are no A's. There's a B. There are 2 C's, but there's no D's. So there's no A's, 1 B, 2 C's, no D's. So that's an example of a string of bars and dots that represents BCC. Let's do another one. Let's go the AAA. So I would have 3 dots, bar, bar, and bar, right? So notice it's just three dots for the 3 A's and nothing else. So for every one of the multisets, I could represent it as a string like this. Now, let's ask a question now about these strings, because now that we've described it in a much simpler way, we could come back to talking about positions in a string and the placement of the dots. Just like in our example that we talked about actually when we were talking about k-combinations, we actually talked about placing ones in a binary string. So we could take the same idea. So how long is a string of dots and lines? So how long is one? Well, let's think about it. So how long is it? Well, you're going to have, okay, how many bars are there? For example here, notice that I have four buckets, right? To separate them, I use 1 less than the number of buckets. Because that means that there's exactly, if I have n buckets, how many lines are there? There's n minus 1 of them. Well, there's n minus 1. So this is the number of bars or lines. Plus k, which is the number of dots, right? We always have k of them in there. Which I'm just going to rewrite as n plus k minus 1. So there's this many positions in the string always. And now that we have positions in a string, and I know how many elements I'm going to pick, do you see how this is actually an exercise about how many ways the dots can appear in the string, because everything else becomes just a bar, right? So it's just the exact same exercise as this. So we select k positions of the n plus k minus 1 many positions. So just to be very clear, you would imagine this as a set that it goes 1, 2, 3, 4, 5, 6, 7, 8, 9, where the last position is n plus k minus 1. And then you ask the question of how many k combinations there are when you select over this set. And that's exactly what we're dealing with. That's just it's just an extra elaboration on this idea. So we select k positions for the k n plus k minus 1 many positions. To place the dots. All others are for bars or lines. Hence, the number of k combinations with repetitions or repeats is n plus k minus 1 choose k. So notice that really, we're really dealing with the same kind of problem, just we have to think about it a little differently. Kind of like our example when we talked about k combinations, we talked about finding the number of 8-bit strings with exactly 5 ones in them. We're actually answering a very similar question to this, just I've recast instead of thinking of a binary string, you can think of it just as lines and dots. Pretty cute, right? Well, I thought it would be a good idea. I summarized, just give you just a little bit of a toolbox just to wrap everything together in a nice bow. So let me just summarize what we've discussed here. So we have some tools other than, of course, the addition and multiplication principles. Thought I would give you a nice little handy table to make this easier. So when choosing k objects, from n objects, we have some different scenarios. So we have it where the order matters and when the order does not matter, right? And then, of course, we have it where we're allowing repetitions or repeats. So repeats allowed versus not allowed. So let's fill in the table, okay, everybody? So first, if order matters and repeats are allowed, what did we have here? This is just a k-step process, right? Where you pick from n objects, n objects, n objects, n objects. You do this k times n to the power of k. However, if the order does not matter, we have the same issue that we had over here. K plus n minus 1, choose k. How about if repeats are not allowed? What about if repeats are not allowed? Okay, if repeats are not allowed and the order matters, what is that? Well, I'm choosing k objects, but I'm not allowed to reuse them. Well, this is just pnk, right? Likewise, if repeats are not allowed, but the order doesn't matter, remember the relationship we had with our k permutations and k combinations? Oh, now we're talking about the number of k combinations. Because remember, repeats are not allowed in k combinations. This is in contrast to k combinations with repeats or repetitions as we derived over here. So this is just simply going to be n choose k. In fact, let me write this just slightly. Make it n plus k minus 1. But yeah, hopefully this helps you a little bit. So remember, as I mentioned previously, when it comes to counting principles, sometimes it's not trivial to count, okay? Sometimes you have to read very carefully the problem, then think carefully about what it means in a combinatorial way, and then see if any of these standard approaches work. And if it doesn't, then maybe it's some conjunction or disjunction of choices that have to be made, whether you use the addition principle or the multiplication principle. So that being said, I want to say thank you so much and have yourself a beautiful day. So are there any questions? Any questions? That's actually the last bit I have to cover here for today. So this covers permutations, combinations, and if people are curious more about this topic, I'm happy to talk more about combinations in relation to other combinatorial structures. So, for example, I point out this weird symmetry that was happening with a number of k combinations. That isn't an accident. That really is what happens all the time. It has this weird symmetry thing going on. It relates to something called Pascal's triangle. And in fact, the power set observation I gave you was just a fun aside. It actually has a relationship also with this too. So, I don't see any questions. It's rather quiet here today, and we have some fun spam in the chat, which always makes things epic as heck. But I don't see any questions. What I was thinking of doing is I'm going to stop right here. If you have any questions, please don't hesitate to leave them in the chat or reach out to me. Of course, the notes will be available after today's lecture. I'll be putting it up, and I'll put up an announcement on Patreon or Subscribe Star. So I'll say thank you so much, everybody, and have yourself a beautiful day. I'll see you later.